welcome to The Explainer. We're surrounded by data, just numbers everywhere. But how do you know if a particular number is a big deal or just noise? Today, we're going to break down how to find the meaning in data to see where any single number truly stands in the crowd. So let's kick things off with a scenario you've probably been in. You're at a theme park, maybe Disney World. You walk up to your favorite ride, Space Mountain, and the sign says the wait time is 45 minutes. Now, is that long? Your gut might have an answer, but how do we actually know?
Well, to answer a question like that, you need one crucial thing: context. A number by itself is pretty meaningless. And in the world of statistics, the tools we use to get that context are called measures of relative standing. They're what let us compare one piece of data to the whole group.
Okay, let's dive into our first and probably one of the most powerful tools in statistics, the z-score. I like to think of it as a universal yardstick. It's this incredible tool that lets you compare things that seem totally unrelated, like body temperature and the weight of a coin. So what exactly is a z-score? It's really simple. It's just the number of standard deviations that a data point is away from the average of the group. It's not about the raw value, it's all about its distance from the middle of the pack. Now, you're gonna see a formula, but don't let the symbols freak you out. The idea is super simple. You just take your value, that's x, and subtract the average of the group, that's x bar. Then you divide that result by the standard deviation, s, which is just a measure of how spread out all the data is. And that's it. That gives you the z-score. Okay, to really see why this is so cool, let's pose a wild question. Which is more unusual? A person with a body temperature of 99 degrees Fahrenheit, or a US quarter that weighs 5.7790 grams? I mean, how on earth could you even begin to compare those two things?
Well, with z-scores, it's easy. We just plug in the numbers. For the body temperature, we get a z-score of 1.29. Then we do the same calculation for the quarter's weight, and we get a z-score of 2.26. Just like that, we've put two totally different measurements on the exact same scale.
And that is the key. The temperature is only 1.29 standard deviations away from its average. But the quarter? It's a whopping 2.26 standard deviations away from its average. The higher z-score tells us, without a doubt, that the quarter's weight is the more extreme, more unusual value of the two. Pretty cool, right? This brings us to a really handy rule of thumb. In general, any z-score that falls between -2 and +2 is considered pretty normal. But once a value's z-score goes past those boundaries, either below -2 or above +2, we start to consider it statistically significant. It's an outlier. So let's put this rule to the test with a new example. Say we have data on earthquakes, and the average magnitude is 2.572. Then a quake hits, that's a 4.01. Is that a significantly high magnitude for this area? Well, let's run the numbers and find its z-score. And there's our answer. The z-score is 2.21. So, what's the verdict? Well, since 2.21 is bigger than our cutoff of 2, we can say, yeah, that 4.01 magnitude earthquake was significantly high compared to the others in its group. Okay, so z-scores are awesome, but let's switch gears to another way of looking at this, one that might feel a little more familiar. We're talking about percentiles and quartiles. You've probably seen these on standardized test results or your kids' growth charts. The idea of a percentile is really just about ranking. It slices the data up into 100 equal chunks. So if you score in the 90th percentile, all that means is that you scored higher than 90% of the people who took the same test. It's that simple. All right, let's jump back to our Space Mountain question. To figure this out with percentiles, we need to see the data. So here it is. 50 different wait times for that ride, all nicely sorted from the shortest wait all the way up to the longest. So now we can finally answer our question. We look for our 45-minute wait time, and we just count how many values are smaller than it. Turns out there are 36 wait times that are shorter. So we take that 36, divided by the total number of waits, which is 50, and multiply by 100. And we get 72. That means a 45-minute wait is in the 72nd percentile. It's longer than 72% of all the other times recorded.
But what if we want to go the other way? Let's say we want to know what wait time marks the 25th percentile. We can follow these simple steps. First, we calculate a locator value, L. In this case, we get 12.5. Since we can't have half a position, we just round that up to the next whole number, which is 13. Then we go to our sorted list and find the 13th value. And there it is. The 25th percentile is a 25-minute wait.
Now, that 25th percentile is so important it gets a special name,
the first quartile, or Q1. Quartiles are just the most famous percentiles. They slice the data into 4 equal quarters. Q1 is P25, Q2 is P50, which you might remember is also the median, and Q3 is P75. Okay, so we've got these quartiles. What do we do with them? Well, they let us build something incredibly useful called the 5-number summary. Think of it like getting the vital signs for your entire data set all at once. And the 5-number summary is exactly what it sounds like. It's just 5 key numbers: the absolute minimum, the first quartile, the median, the third quartile, and the absolute maximum. For our Space Mountain data, that's 10, 25, 35, 50, and 111. In just those 5 numbers, you get a fantastic snapshot of the whole picture.
And now for the grand finale. We can take that super simple 5-number summary and turn it into an elegant and really powerful picture called a box plot. Making a box plot is actually really simple. You start with your 5-number summary. You draw lines, or whiskers, that go from the minimum to the maximum. Then you draw a box that stretches from the first quartile, Q1, to the third quartile, Q3. And the last step is to draw a line right through the box at the median. That's all there is to it. And here it is, the finished product for our wait time data. In this one picture, you see the whole story. The whiskers show you the full range, from 10 all the way to 110 minutes. The box itself shows you where the middle 50% of wait times are, between 25 and 50 minutes. And that line in the middle tells you the median wait time is 35 minutes. It's so much information in such a small space. But this is where box plots really shine. They don't just summarize your data, they can actually show you its shape. Check it out. A symmetrical, bell-shaped data set gives you a nice, even box plot. But if your data is skewed, the box and whiskers get all stretched out on one side. You can tell so much about your data just by looking at this one simple chart. So the next time you see a number all by itself, I want you to remember to ask the most important question: compared to what? Because now, with tools like z-scores, percentiles, and box plots, you have everything you need to find the answer and to really understand the story your data is trying to tell you.